Hi, today I'm going to introduce a concept, MP-adaptive video streaming over preference-aware multipath. As we all know, video streaming has become one of the most critical applications on mobile devices. A recent study indicates that video accounted for 55% of total mobile traffic in 2015, and this percentage will increase to 75% by 2020. However, mobile users' quality of experience for video streaming is still often far from satisfactory, especially under challenging network conditions such as unstable Wi-Fi connectivity and mobility. And the research also found in about 80% of locations, their open Wi-Fi does not provide stable throughput for streaming in a high-quality video, while the combined bandwidth of Wi-Fi and cellular almost always does. So although LTE may be enough at most locations, users may want to limit their cellular data usage. So that could be a concern as well. And there is a potential solution that might solve the problem. It's called MPTCP. MPTCP is a standardized multipath solution allowing applications to transparently use multiple paths. MPTCP has already been implemented in Linux kernel. However, it has no ability for users to specify their preference of how to utilize wireless interfaces. Instead, the path utilization is mainly determined by the MPTCP scheduling algorithm. This paper also measured the throughput and RTT of the Wi-Fi networks at 33 locations in 3 far apart US states. And the results implies that in the real world, it is very likely the public Wi-Fi itself cannot provide the best video streaming experience. And also at the time of this paper published, 2016, it was a main problem, especially in public Wi-Fi condition, which is not good enough for quality of experience. So after 2 years streaming, like video streaming development, nowadays, it is still a problem. Poor connection and limited bandwidth will impact the streaming quality dramatically. So this paper proposed a system called MP-, which is a novel multipath video streaming framework. And the overall goal of MP- is to add MPTCP support to dash video streaming under user-specified interface preferences. So an MP- consists of 2 main parts. The first one is called MP- scheduler, and second called video adapter. The MP- scheduler takes as input the interface preference from users, as well as video chunk size and delivery deadline from the video player. It then intelligently determines the best fetching strategy of the video chunks over multipath path by leveraging their delay tolerance nature. The MP- video adapter is a lightweight add-on that makes an existing off-the-shelf dash algorithm multipath friendly. So for the implementation of MP- scheduler, MP-scheduler as an overlay of MPTCP. So it serves as a building block for multipath friendly video streaming. In addition, it can benefit a wide range of other applications with delay-tolerant transfers. So, and also the paper studied 2 representative categories of dash rate adaptations. First one is throughput-based, and second one is buffer-based, and proposed solutions for them to effectively use MP- with only like 30 to 100 lines of code change. So for the MP- system design, there are 3 major requirements for MP-. First, MP- should be able to accommodate the interface preferences specified by users and schedule the video delivery based on the preferences. Second, there needs to be a mechanism for video-specific information to be exchanged between the video player and the MP- framework. Last, the overall system needs to be scalable and lightweight. So when we look at the picture on the left-hand side, this is the whole structure or the architecture of the MP- system design. And it consists of 2 key components, the MP- scheduler and the MP- video adapter. So as shown in the figure on the left side. So in the picture, it's called deadline aware scheduler. It's another the kind of the algorithm of the scheduler. The scheduler enhances MPTCP in two aspects. First of all, it is aware of the preference of multipaths. Second, it is aware of the deadline of each video chunk. So as we can see, that arrow point from adapter to scheduler includes chunk size and deadline. So by using this piece of information, the scheduler strategically manages the network paths with the goal of meeting deadlines while satisfying user-specified preference. The MP-video adapter is a lightweight add-on that makes existing dash algorithms multipath friendly. And the adapter is lying in the middle between the original dash algorithm and the MP-scheduler. Its main job is to inform the MP-scheduler through a unified interface of each chunk size and deadline. So for the interface of MP-scheduler, it consists of two parts. First, the scheduler offers a socket option, MP-enable, to convey the data size S and the deadline D from the user space to the kernel. And the second part of the interface enables a dash adapter to obtain necessary information for rate adaptation. And this interface is needed because video player does not have the visibility of the network condition of all network paths, since MPTCP is oblivious to the player. And now we consider the function split between client and the server of the scheduler. The MP-scheduler should ideally run at the video streaming server where it can directly distribute traffic onto different paths. However, a video server does not run the dash logic, and thus the MP-adapter should reside on the client side. We thus split the scheduler into two parts: the decision function on the client and the enforcement function on the server. The decision function determines how to manage the paths. So, for example, whether the cellular subflow should be enabled based on the information from the video of a player, and notifies the enforcement function of the decision using a reserved bit in the MPTCP option. This design makes MP- scalable as the server side becomes stateless. So now we consider the interface for the user. Because the user can make their choice, make their preferences, and as a self-contained framework, MP- allows users to specify the multipath policies such as interface preference. And now we look at the deadline-aware MP-scheduler, which we just saw in the figure. A deadline-aware MP-scheduler that takes both the interface preference and the delay tolerance nature of video traffic into consideration. The preference can be quantified by cost associated with each path. The cost could be data usage, energy consumption, or a combination of both. So configured either statically or dynamically, the goal of the MP-scheduler is to meet the playback deadline of a chunk while minimizing the overall cost. So the deadline awareness has been investigated in various scenarios such as base station scheduling for multimedia traffic and data center TCP. Different from existing works, MP- targets a dash video delivery over multipath. In short, the overall goal of the MP- scheduler is to minimize that cost function, which is in the right side of the screen. So now we look at the second part, MP-video adapter. So why do we want the video adapter? The reasons why we need adapter is that there are two reasons. First of all, the interaction between the dash rate adaptation algorithms and the MP-scheduler is complex. So in particular, there exists a control loop. MP-scheduling decision will affect dash rate selection, which in turn impacts MP- scheduling through setting of chunk size and deadline. This is quite different from using the MP-scheduler to download a single file where the application and scheduler are very loosely coupled. And the second reason, there are many dash read control algorithms. Ideally, we want to plug the MP-scheduler into them in the same manner. And it's hard to plug scheduler into different dash read control algorithm in same manner without the video adapter. And we found due to their different read adaptation logics, dash algorithms incur different cross-layer interactions with the scheduler. This inevitably requires modifications to dash algorithms at a category-by-category basis, although we try to minimize the changes. And now I'm going to introduce some logic of the read adaptation. So I'll first provide the background of read adaptation algorithms for Dash. In a Dash system, a video is split into multiple chunks of the same playtime, and each video chunk is encoded with multiple discrete bit rate levels. A video player can switch between different bit rate streams at the chunk boundary. As the chunks are time-wise aligned, thus it requires an algorithm to select the chunk's bitrate for achieving an optimal qualitative experience. There are largely two categories of dash rate adaptation algorithms: throughput-based and buffer-based, which is mainly discussed in the paper. And the hybrid dash rate adaptation is for the future work. The throughput-based adaptation adjusts the encoding rate of chunks based on the estimated throughput, which indicates the future network capacity. For instance, buffer-based adaptation, BBA, chooses the bitrate based on a video player's buffer occupancy level, which implicitly encodes information of the network capacity when the video playing is at the steady state. And we look at the second one called buffer-based dash rate adaptation. We then shift to the buffer-based rate adaptation, which maps the buffer occupancy to video qualities. The intuition is that the buffer occupancy implicitly encodes the relation between the network capacity and the selected video bit rate. For the hybrid dash rate adaptation, instead of solving an optimization problem for each chunk, its online version looks up a pre-generated table to select the optimal bitrate based on the buffer level, previous bitrate, and throughput estimation. To support MP-, MPC can set a chunk's deadline as the chunk size divided by the minimum throughput required by the optimal bitrate known from the table. Meanwhile, since MPC is a hybrid approach of using both throughput and buffer occupancy for rate adaptation, however, the detailed design is left for the future work. So, in conclusion, there are a few points of view. First of all, for the performance of MP-scheduler, the paper did some experiments over real Wi-Fi and LTE, and all data transfers finished before the deadline, and the average finish time is close to the deadline. However, under the scenarios with high bandwidth prediction errors, the deadline may be missed, but it can be prevented by applying an optimal algorithm and by setting hyperparameters like alpha. And for controlled experiments, the paper investigates 4 dash algorithms: FASTIV, GPAC, and BBA that we talked about earlier, and BBAC, with and without MP-. And the paper observes no stalls in all experiments, and MP- has no impact on the average playback rate. Thus, the paper focuses on metrics of cellular data usage and radio energy consumption. The figure on the right of the screen plots the distribution of cellular data savings brought by MP- for 4 streaming schemas. The results demonstrate MP- can effectively reduce the cellular data usage and radio energy for dash video streaming over multipath, compared with using the vanilla MPTCP. So compared with players with off-the-shelf MPTCP, the framework can dramatically reduce the cellular data usage and radio energy consumption without sacrificing users' quality of the experience. So, thank you.